Hello, this is Deborah Barrett with the Cincinnati State Physics Department showing the conclusion of our sample problem for the component method of adding vectors. This video picks up where part 1 left off. You can see we've drawn the original vectors in solid black. We've drawn the axes in dotted line black. We've drawn guidelines for the components in dotted line black, and the components themselves are drawn in color. We've used blue for one set of components, green for another set of components, and red for the third set of components. I have also found the size of the components and marked them onto the diagram alongside the associated component and color-coded to match the vector arrow for the color component. So my blue components of 13.8 meters in the y direction and 31.1 meters in the x direction would add up to give us 34 meters if we combine them at a 24-degree angle using vector addition, which would require Pythagorean theorem and a little bit of trig. Since they're perpendicular, we could add that 13.8 meters and that 31.1 meters just by using Pythagorean theorem and trig. And if we did that, the two blues could take over for the 34-meter original vector we had there. That means that we could erase out the 34 meters at this point and simply work with the two blue vectors in their place. Similarly, the two green vectors, the 43.0 meters in the x direction and the 61.4 meters in the y direction, would add together using Pythagorean theorem and trig to give us 75 meters in the 35-degree direction. That means that the two greens can take over for the 75 meters, and so we can take the 75 meters out of the diagram and not worry about it anymore. And finally, since the two red components would add up vectorially to give us 130 meters at 42 degrees down from the negative x-axis, we can also take out the 130 meters. Now, that means that if we added up the colored components that are still shown, that would be equivalent to adding up the original black vectors that we just erased. And hey, it's not so hard to add up the colored components. First, we add the components that are shown along the x-axis. We have a 96.6 meters shown to the left in red, a 31.1 meters shown to the left in blue, and a 43.0 meters shown to the right in green. Since the 43 meters is in the positive direction and the 31.1 meters and the 96.6 meters are in the negative direction, we can add those three up just by keeping those signs. So I've shown in the bottom half on the left that the sum of the x's will be 43 meters minus 31.1 meters minus 96.6 meters. When we add these x components up, we get negative 84.7 meters, or 84.7 meters overall in the x direction, the negative x direction. Now we repeat the process with the y component vectors. We have a 13.8 meters in the positive y direction, shown in blue on the diagram. In the negative y direction, we have the green 61.4 meters and the red 87.0 meters. So next we add those up to find what our total of the components is in the y direction. I've shown the summing of those y components now underneath the sum of the x components. they work out to negative 134.6 meters. The next thing you want to do in order to really get a feel for what's going on with these vectors is to make a new sketch showing that total x and the total y tails together in a new sketch. So here are my two summation vectors. I've got my 84.7 meters in the negative x direction, and I have my 134.6 meters in the negative y direction. I've drawn those with their tails together, just like I drew all the original vectors and components, and I have labeled them each with their magnitude and put an arrowhead on each. These two total vectors, the total x and the total y, came from the colored components that we had in the prior sketch, and those colored components came from the original vectors that we were trying to add. So if we add up this 84.7 meters and the 134.7 meters, we will have the same total as we would have gotten from adding up the original three vectors. If you've drawn vectors with their tails together, the resultant can be drawn by going from the joined tails diagonally across the parallelogram that's made from the two input vectors. I want to see the resultant of these two vectors, so I'm going to draw a parallelogram made from these two vectors. We know that a parallelogram has four sides, two pairs of parallel sides. So I'm going to start at the tip of the 84.7 meter vector, and I'm going to draw on down parallel to the 134.7 meter vector. There's my parallel side running from the tip of the 84.7 meters, pretty much parallel down parallel to the 134.7 meters. Now, likewise, I'm going to go to the tip of the 134.7 meters and draw parallel to the 84.7 meters. Now that I've drawn those two parallel sides, we can see that the figure I wind up with works out to be a rectangle because the two components that I was dealing with were perpendicular to each other. If the original two input vectors were not perpendicular, then we would have a generic parallelogram that would look more like a twisted picture frame. However, on this one we've got a rectangle, and as I said a moment ago, the resultant of two vectors, if they are drawn with their tails together, runs from the joined tails diagonally across the parallelogram made from those two input vectors. So next I'm going to draw my resultant from the joined tails of these two vectors diagonally across. I often like to draw that resultant with a contrast color like I've drawn here to make it stand out. Next, I'm going to put the arrowhead on this resultant to remind me that the resultant goes from the joined tails out diagonally across the parallelogram that was made. So there's my arrowhead, and there's my resultant, and I'm also going to label it that that's the resultant. So to find the resultant for the whole problem, all I have to do is find the resultant in this final figure. Well, gee, once we've drawn it this way, it's pretty obvious that to finish up we need Pythagorean theorem and a little bit of trig to get the angle. So that's how we're going to complete this. Pythagorean theorem, of course, says that a squared plus b squared equals c squared if you have a right triangle. Well, since we drew a parallelogram based on two perpendicular vectors, that means we've got a couple of right triangles. The resultant, which is drawn in red, would be the hypotenuse. So I'm going to set up my Pythagorean theorem as, let's see, I'll use my x's for my a's. So I have 84.7 meters quantity squared plus 134.6 meters quantity squared equals my resultant squared. I'll just go ahead and figure out what that gives me for the magnitude of my result. I now have a magnitude of 159 degrees for my resultant. The resultant means the one vector that gives the same result as combining all the other vectors. So that tells me the effect, size-wise, of adding up those two vectors. Next, I need the direction for that resultant. Direction should always be measured at the tail of the vector that you are checking. So this red vector resultant needs to have its direction assessed at the tail. There are two angles I can choose from at the tail. One is here, and the other is here. Either one will work fine because we're going to have to stipulate which axis we're measuring from. I'm going to arbitrarily choose the lower angle, the one that's measured off of the y-axis. So I'm going to think about the trig I need to set that up. I've erased out the angle that I decided not to use so that I can focus on that lower angle measured from the y-axis. Now, this drawing was a rectangle, so I know that my 84.7 meters along the x-axis is the same size as the bottom edge of my rectangle. I think I'm going to label that as an 84.7 to try and keep me on track. Once I do that, I can see I have a right angle, and I know the two legs, and I want the angle. The relationship that would be relevant here would be the tangent, because tangent equals opposite over adjacent. In this case, we don't need to solve for a side of this triangle. We need to solve for the angle. So I'm going to go ahead and fill in the magnitude of the opposite side and the magnitude of the adjacent side. Since the angle I chose to work with is measured against the y-axis, that means the opposite side is the 84.7 meters. So I have filled that in for my opposite, and the adjacent side is my 134.6 meters. Now, these two units are going to cancel. So with those units canceled, I divide my 84.7 by my 134.6. That gives me a tangent of 0.6293. That, of course, is not what I need. I need my angle theta. So I will take the inverse tangent, or the arctan, of 0.6293 on my calculator. That gives me 32.2 degrees, which I have now marked in my figure where my angle is. It seems like we're almost done, but not quite. We have a resultant magnitude of 159 meters, as we had already determined. And it's tempting to say the direction is 32.2 degrees, but that wouldn't really be correct. Since our original problem was measured off a 0-degree angle, or the problem said to consider 0 degrees to be east, if we give an angle of 32 degrees, that means 32 degrees north of the eastward direction. And when we look at this diagram, we can certainly see that that red resultant is not pointing north of the eastward direction. It's 32 degrees from south, 32 degrees specifically west of the southward direction. So if we want to give our answer in terms of compass points, that would be a direction of 32.2 degrees west of south. Alternately, if we wanted to give the direction In terms of a 0-degree reference line, we would use the fact that this red vector resultant is 32.2 degrees short of the 270-degree axis. So the direction would be 270 degrees minus 32.2 degrees, or 237.8 degrees measured from 0. If the vector problem was originally stated with compass points, we would want to answer with compass points, 159 meters at 32.2 degrees west of south. If the vector problem is originally stated with measurements given from 0 degrees, then we would give the answer as 159 meters at 237.8 degrees. So we answer consistently with the problem statement. Because this problem statement talked about taking 0 degrees to be east, we could answer either way. Thank you for reviewing how to add vectors with the component method. Hopefully this will help with your work in Chapter 3 and going forward in the course.